So introducing our first speaker here, we have Richard Wohler with GPI Geospatial. The presentation is called Aerial and Mobile LiDAR Solutions for Pavement Surface Elevation and Rating, PASER. Richard has worked for GPI Geospatial in the Wisconsin office for 37 plus years. He has also been actively involved with WLIA for 25 plus years. All right, Richard, take it away.
Richard, do you have any words of intro or should I hit play?
Just go ahead and hit play, Joe.
All right, here we go.
Good afternoon, everyone. I am very pleased that the WLIA invited me to give a virtual presentation. My presentation today for the 2021 WLIA Virtual Annual Conference is on aerial and mobile LiDAR solutions for pavement surface evaluation and rating, or otherwise known as PASER. PASER analysis is developing into an essential discipline to determine whether interstate, state, or county highway routes require maintenance, resurfacing, or complete construction replacement. In this presentation, we will review the different types of defects, deformations, cracks, and surface loss of pavement that can occur on asphalt and other types of surfaces along highway corridors. This will include a rating system to quantify these distress problems that will ultimately determine the best solution to fix the surface and/or substrate distress conditions. LiDAR, whether aerial or mobile, is fast becoming a mechanism to detect and map pavement surface deformations. We will explore the planning of a LiDAR aerial acquisition and a mobile LiDAR drive plan and show how these platforms can be used to accurately depict and map these deformations. Before we get into the PASER presentation, though, I would like to tell you about GPI Geospatial. GPI Geospatial is a national multidiscipline geospatial mapping firm. We have 9 offices located along the eastern seaboard and upper Midwest. Our corporate headquarters is located on the Executive Orlando Airport in Orlando, Florida. I conduct my business development activities out of our Sheboygan, Wisconsin office. We have 3 aircraft and 2 mobile LiDAR acquisition and processing vans which can deploy to any one or multiple offices for project acquisition. Currently, we have 2 of the premier Regal 1560 Mach 2 aerial LiDAR sensors and 1 UltraCam Eagle for the fixed wing acquisition of precision aerial LiDAR and aerial imagery. Our mobile systems are both equipped with the Regal VMX 450 LiDAR sensors to provide design-grade surface models for transportation corridors. These vans have dedicated workstations and storage units which can process data remotely and act as mobile workstations. GPI provides geospatial mapping services to multiple vertical markets, including the federal government, state and local agencies, private industry, utility companies, and transportation agencies such as state DOTs. Our axiom is GPI, many talents, one firm. Our staff is comprised of expert personnel with geospatial certifications to ensure a quality mapping product is delivered on time, every time, and within the project budget. These include multiple certified photogrammetrists, public land surveyors, certified survey technicians, certified mapping scientists, and GIS professionals. The topics of this presentation include an introduction to PASER, common asphalt distress categories, PASER asphalt condition ratings, practical advice on rating roads, aerial LiDAR acquisition, mobile LiDAR acquisition, LiDAR processing, both aerial and mobile, project examples, PASER analysis to condition ratings, and finally a presentation conclusion. We will explore these topics to provide a better understanding of how geospatial LiDAR applications can identify and facilitate PASER engineering studies on interstate, state, and county highways. The initial 4 topics will lean heavily on the article PASER Manual for Asphalt Roads, published by the Transportation Information Center at the University of Wisconsin-Madison. This manual was published in 2002 with the most recent updates in 2013. Since this manual is copyrighted, each slide containing content from the manual will be attributed to the Transportation Information Center. What is PASER? The industry definition of PASER is Pavement Surface Evaluation and Rating, which identifies a series of asphalt surface distress categories, a numerical rating on asphalt pavement surface conditions, and practical advice on procedures to inspect, average, and assess these distress and deformation conditions. There are many factors which contribute to the surface distress and deformation of asphalt pavement. Factors such as traffic volume and type, climate, for example northern temperate, temperature, drainage, applied asphalt mixture quality, whether superior, average, or poor, substrate, asphalt road construction methods, and age all contribute to the deterioration of asphalt roadway surfaces. Everyone listening to this presentation has driven a country or state highway with tire rutting, cracking, and/or potholes. Not only are these deformations an eyesore, but they are also a public safety hazard. I can, off the top of my head, think of several accidents I have heard of in the past due to a vehicle hitting a severe pothole or crack in the pavement. My own experience of driving on the interstate in Illinois was an eye-opener. While driving the interstate, I was changing lanes where deep and wide centerline cracks, over 2 inches wide, existed between the lanes. My SUV at 70 miles per hour lurched violently during the lane change. This type of surface distress could easily cause an inexperienced driver to have a single or multiple car accident. Further, the general population, especially commuters who are driving every day, can experience higher than normal maintenance on their car suspensions due to these distress and deformation conditions. This slide depicts several of the asphalt pavement deformation and deterioration conditions, including cracks, rutting, and potholes. First, let's look at the common asphalt pavement surface distress categories. There are 4 major categories of surface distress. First, surface defects. This includes raveling, flushing, and polishing affecting only the asphalt material on the surface. These types of defects are not readily noticeable to the public while driving. Have you ever heard some continuous road noise from your tires while driving on asphalt? This is a result of this type of surface defect, and it does inflict excessive wear on your tires over long periods of time. The second type is surface deformation. Rutting, distortion, rippling, and shoving, settling, frost heave, all affecting the asphalt structure without significant surface breakage. These types of deformation affect the road surface to the point the driver can feel like their vehicle is almost steering itself while in a lane tire rut. It can create that washboard shudder which will shake the entire vehicle, or in heavy rain conditions can result in hydroplaning, with consequences that a driver has partial loss of steering control and braking. Very dangerous. The third category is cracks. Transverse, reflection, slippage, longitudinal, block, and alligator cracks, which all affect the asphalt structure. Cracks in the pavement can be composed of many different forms and usually are felt only as slight bumps as the vehicle traverses them. Cracks are typically only an annoyance unless they are large cracks or there are multiple cracks in a small area, which may result in the asphalt breaking away from the substrate, either in small or large areas. The fourth category is patches and potholes. Patches are temporary fixes to major but localized damage to the surface. Potholes are major holes in the asphalt structure down to the substrate. Patches are similar to cracks in that they only are slightly noticeable as the vehicle traverses them. Patches can be applied to potholes or can traverse the entire road from edge of pavement to edge of pavement and can be any size and configuration. Potholes occur when small sections of the asphalt dislodge from the substrate and leave a small, or in some cases, large hole in the driving surface. Countless vehicle suspensions have been broken due to potholes, and in the extreme, potholes have caused serious accidents with driver-passenger injuries and even death. The next series of slides will display individual surface distress types within the 4 major categories. All source images are from the Transportation Information Center. Surface raveling is a variable loss of smaller aggregate exposing the tops of larger aggregate. Slight raveling is the beginning stage of asphalt decay and makes the surface similar to rough sandpaper. If you ever have taken a walk on a paved country road, walking on this type of surface will slowly become tiring to the individual. Moderate to severe raveling results in a very coarse but consistent surface with pitting as the surface loses larger pieces of asphalt and aggregate. This type of surface can be painful to walk on barefoot for long distances. Severe raveling results in large portions of the asphalt and aggregate surface worn away to varying degrees. The surface is uneven with extensive pitting. At highway speeds, can you imagine how this surface is affecting your tire wear and life? When a highway surface reaches this level, either resurfacing or replacement is mandatory. Surface flushing is caused by poor asphalt mix or seal coating over a flush surface. This is readily apparent by dark patches where asphalt has worked to the surface. This surface has a tendency to wear quickly under heavy traffic since very little aggregate is inhibiting the surface from wear. Surface polishing is caused by traffic wear off sharp edges of aggregate. The surface of the asphalt becomes excessively slippery, and vehicle tires can almost react in a similar fashion in extreme conditions to being on ice during the winter season. Again, very dangerous. Surface rutting occurs when asphalt is displaced by traffic compaction, a poor asphalt mix, or displacement of substrate material. Traffic compaction causes most rutting on older county and state highways due to poor or inadequate substrate. The most dangerous conditions concerning rutting occur during heavy rainstorms. Vehicles can hydroplane and lose traction with the road surface. Further, braking can also become a greater issue. Slight surface rutting is easily identifiable during rain events. A continuous pool of water will exist in the lane in the direction of traffic travel. Slight rutting can cause issues, but does not always dictate resurfacing or replacement. Severe surface rutting can result in actual road humps in the lanes in the direction of traffic travel. This is excessively dangerous during rain events and when traffic is changing lanes while traveling on the highway. This excessive humping requires immediate replacement of the asphalt surface and possibly the substrate. Severe surface rutting due to poor substrate can create asphalt that is sinking lower in the road primarily due to traffic compaction. As with other types of rutting, safety becomes an issue and only full replacement of the substrate and asphalt will resolve the issue. Surface rutting, whether slight or severe, is a public safety hazard, and measures to rectify the road structure should be taken as soon as possible. Surface distortions occur from shoving, rippling, settling, or frost heave of the asphalt surface. Shoving or rippling of the asphalt surface occurs perpendicular or crossways to the direction of traffic as shown in the upper left. Poor asphalt mix and external roadside pressures will form these ripples that can develop into washboarding, which is not only an annoyance, but also a public safety hazard, since a vehicle is difficult to control when the suspension and tires are repeatedly jumping in an attempt to mitigate the undulating surface. Frost heave occurs due to water collecting under the asphalt or substrate and freezing during the winter months. Since water expands when frozen, the substrate and/or asphalt is pushed up, creating a small mound in the road surface. This is a common occurrence in northern regions of the United States and can create a whole host of issues such as potholes and cracking of the asphalt surface, to name a few. Traverse cracks form at right angles to the center line, are usually regularly spaced, and are caused by temperature change and hardening of the asphalt. Traverse cracks are typically widely spaced, but can be at shorter intervals. This can result in a series of open cracks perpendicular to the direction of traffic flow, 1/2 inches or larger in width. Water can then seep into the traverse cracks and create secondary cracks. A further manifestation of this type of cracking is pavement raveling and erosion along the traverse cracks. Reflection cracks occur when the crack pattern of the pavement underneath or substrate base is reflected by cracks in the surface asphalt layer. A typical example of this is when concrete joints cause cracks in the asphalt surface. In many instances, the cracks will be very linear in direction of the traffic flow or perpendicular to the direction of traffic flow. This is one of the more difficult crack patterns to prevent and usually requires a complete replacement of the substrate and asphalt overlay. Surface slippage cracks occur when there is a slippage between the overlay and the substrate and appear as crescents or rounded cracks in the direction of traffic flow. Slippage cracks commonly occur at intersections due to traffic starting and stopping. When left unrepaired, water and vehicle traffic can further deteriorate the asphalt coating, resulting in bond loss in the asphalt surface, pitting, and ultimately small or large potholes. Longitudinal cracks form in the direction of vehicle traffic, can develop in the center line, along the outside edge of the travel lanes, or in the lane wheel paths. Centerline cracks occur when there is inadequate bonding during construction or reflection cracks in the substrate. Edge cracking within 1 foot of the pavement edge is due to insufficient shoulder support, poor drainage, or frost action. Edge crackling can also occur in the lane as a result of weakened substrate and traffic loads. Wheel path cracks are created by heavy traffic loads over long periods of time. Block cracks form as interconnected cracks creating large blocks at nearly right angles ranging from 1 foot to 10 foot or more in size. Large block cracks can be 6 foot to 10 foot or more in size. Intermediate block cracks are usually 1 foot to 5 foot in size. In some instances, there can be extensive block cracking with a variety of sizes. The more extensive block cracking is an indication of advanced aging of the asphalt surface. Alligator cracks are interconnected cracks from 1 inch to approximately 6 inches that are due to a failure in the asphalt surface substrate and traffic load. This type of cracking can occur in large swaths or in localized areas. Alligator cracks are typically in a type pattern. 2 more types are chicken wire cracks and raveling alligator cracks. Patches are temporary or semi-permanent repairs to fix failures of any type in the asphalt surface or repair for utility excavation. Everyone has seen those long asphalt patches crossing from edge of pavement to edge of pavement, indicative of a utility excavation and repair to the asphalt surface. Edge wedging patches are installed where extensive deterioration of the road edge occurs, but the central asphalt surface is still intact. The central bottom image depicts a highway lane with extensive patching, cracking, and raveling. I think we can all agree that any highway in this shape needs to be completely replaced by resurfacing or all new construction. Potholes occur when there is a loss of pavement material caused by traffic loading, fatigue, and/or inadequate strength. Single small potholes are annoying bumps as we drive down the highway. Multiple potholes show pavement failures due to poor substrate, frost heave, or poor drainage. Large isolated potholes will extend not only through the asphalt surface, but into the substrate. Large potholes also have a variety of cracking types occurring in the adjacent asphalt surface. Large potholes result in further deterioration due to traffic pressure and water incursion causing frost heave. There are 3 components to surface condition ratings. The first is pavement conditions versus pavement age. The age of the pavement is a major factor in the condition of the asphalt surface. Second, surface rating system. This system is set up as a declining numerical system with newly constructed pavement at a rating of 10 down to pavement requiring complete reconstruction at a rating of 1. The third is practical advice on rating roads. Recommended methods to complete the rating for asphalt surfaces include inventory and field inspection, averaging and comparing sections, assessing drainage conditions, and planning annual maintenance and repair budgets. Pavement conditions have a direct correlation to the age of the pavement. Pavement is subject to deformations and cracks as it ages due to multiple factors. Although this seems self-evident, many factors contribute to the decline of asphalt pavement. Quality of construction, rain, snow, salt applications, traffic volumes, to name a few, affect the condition of asphalt pavement. And once deterioration begins, this decline becomes accelerated. After cracking or potholes appear, especially in northern climates, moisture seeping under the pavement can result in frost heaving. Extreme heat can soften the asphalt and, coupled with heavy traffic volume, create lane rutting and distortions. The graph shown here illustrates the pavement aging process in relationship to the rating of the asphalt surface substrate. New pavement receives a rating of 10 and is, of course, in excellent condition. As the pavement ages, it changes to a rating of 6 in good condition, then a rating of 4 in fair condition, and finally, very old pavement will have a rating of 2 or less in very poor condition and requires complete reconstruction. An established rating system is used to evaluate overall conditions of the asphalt surface, dictating the level of needed maintenance or repair. Ratings at the high end require little or no maintenance or minor fixes. Ratings in the middle require some preservative treatments but can be repaired. Ratings at the low end require extensive maintenance, structural improvements, or total reconstruction. The proper review and rating of asphalt pavement for a given corridor will determine the correct application, repair, or replacement. We'll now look at examples of highway sections at the various surface ratings. Ratings 10 and 9 are newly constructed and recently overlaid asphalt roadway conditions, respectively. These rating levels require no maintenance. These types of corridors generally do not require inventory or field inspection. Ratings 8 and 7 are very good and good asphalt roadway conditions, respectively. Rating 8 requires little or no maintenance. Rating 7 typically requires routing crack sealing. These ratings are the initial stages of deformation and stress and require minimal maintenance and almost always do not require replacement. Ratings 6 and 5 are good and fair asphalt roadway conditions, respectively. Rating 6 should consider a preservative treatment. Rating 5 requires a preservative treatment. These ratings occur on moderately aged corridors and are still primarily repairable with preservative treatments. Ratings 4 and 3 are good and fair asphalt roadway conditions, respectively. Rating 4 requires a structural overlay. Rating 3 requires a heavy structural overlay of 2 inches or more. These ratings present a perplexing choice, a structural overlay or complete replacement. The overlay can provide a lower cost solution, but can be considered a band-aid solution to a highway corridor with a degrading substrate. Ratings 2 and 1 are very poor and failed asphalt roadway conditions, respectively. Both rating 2 and rating 1 requires complete reconstruction. These ratings almost always require a complete reconstruction of the highway corridor to maintain public safety. The practical advice on rating roads is divided into 4 steps. The first is inventory and field inspection. includes annual inspections and observations of roadway conditions in the field, which is developed into a written inventory. The second is averaging and comparing sections. Rural roadways are divided into half-mile to 1-mile segments. Urban roadways are 1 to 4 blocks or more. A level of averaging is required to determine the correct rating for the overall corridor. The third is assessing drainage. Proper drainage at the planning stage will ensure the asphalt surface will perform for an extended period of time. Existing roads may not have proper crowning, substrate, ditch construction, culverts, surface or lateral drainage to maintain the asphalt surface in good condition. The fourth step is planning annual maintenance and repair budgets. Normal planned maintenance or rehabilitation procedures can facilitate the use of the rating system, but considering safety, traffic projections, original construction, and pavement strengths may dictate a more comprehensive repair than the rating suggests. Repair budgets will be based on the recommendations from the rating assessment. Now we'll turn to the aerial and mobile platforms for geospatial acquisition of data to support PASER analysis. Aerial LiDAR can be used for PASER analysis, but the optimal platform is Mobile LiDAR. First, we'll review the sensor and planning for aerial LiDAR. To evaluate the potential of an aerial LiDAR acquisition to address PASER applications, we'll look at a 3.25-mile segment of County O in Sheboygan County. This sample corridor has been buffered 50 feet each side of the center line in order to cover the primary pavement surface and intersections. Why County O? It is typical of a county highway in a rural area and allows a simple aerial LiDAR flight plan for this presentation. The LiDAR acquisition data suitable for PASER analysis requires the use of a precision aerial sensor. GPI deploys a Regal VQ1560 Mach 2. The 1560 Mach 2 is the latest and most powerful aerial LiDAR sensor available from Regal. This new ultra-high performance, fully integrated and calibrated dual-channel airborne mapping system makes use of Regal's sophisticated waveform LiDAR technology, enabling an excellent multi-target detection capability and multi-time around processing. The system is capable of online waveform processing as well as full or smart waveform recording, resulting in unsurpassed information content on each single target. The sensor provides a laser pulse repetition rate of up to 4 MHz, resulting in more than 2.66 million measurements per second on the ground, and typical operating flight altitudes ranging from 1,500 feet up to 12,100 feet, producing a wide range of point densities. The sensor is equipped with a Phase 1 IXU RS 1150 megapixel RGB digital camera, which is mounted in the sensor head and can provide simultaneous acquisition of LiDAR and imagery in a single flight pass. Other types of sensors, such as the Optics Galaxy, can be used in the same capacity for this purpose as a Regal 1560 Mach 2. Using the Regal 1560 Mach 2 aerial sensor, the flight plan to support PASER analysis for the County O corridor is displayed below. The flight altitude at 2,000 feet above ground level will provide a single pass point density on the pavement surface of 75 points per square meter. It is possible to increase the point density to 100 points per square meter by lowering the flight altitude to 1,500 feet above ground level with the proper aircraft speed. The higher the point density, the easier it is to detect surface defects, deformations, and cracks. You'll also notice the flight plan includes aerial imagery exposure stations for the Phase 1 camera equipped in the sensor head. When attempting to analyze surface defects, deformations, and cracks, having imagery is another integral tool in the detection process. Additionally, detection of surface defects, deformations, and cracks will not require any field work or targeting. Using the GNSS from the airborne GPS results, sub-meter accuracies can be achieved. For this type of analysis, This accuracy is more than sufficient for PASER analysis. Next, we'll look at the sensor and planning for a mobile LiDAR acquisition. For comparison purposes, we'll use the same 3.25 mile segment of County O, buffered 50 feet either side of centerline, covering the primary pavement surfaces and intersections. The mobile LiDAR acquisition data for PASER analysis requires very high density points per square meter from a precision dual sensor array. GPI deploys a Regal VMX 450 in a van configuration inclusive of onboard downstream processing mobile workstation systems and storage. The VMX 450 integrates two Regal VQ 450 laser scanners as well as inertial measurement and GNSS equipment housed under an aerodynamically shaped protective cover. Each of the two Regal VQ 450 laser scanners provides low-noise gapless 360-degree profiles at a measurement rate of 550,000 measurements per second and a scan rate of up to 200 profiles per second. This will result in a capture rate on the pavement surface of up to 1,000 points per square meter. This is the optimal configuration to detect surface defects, deformations, and cracks for PASER analysis. The van is also equipped with precision Nikon cameras at all four corners that are synchronized to the vehicle speed to capture high-resolution imagery every 15 seconds at standard highway speed. Additionally, forward and rear-facing GoPro video cameras take continuous video capture while the VMX 450 sensor is actively acquiring LiDAR data. Using the VMX 450 mobile LiDAR configuration, the drive plan to support PASER analysis for the County O corridor is displayed below. The drive plan consists of two passes along the corridor, with the first pass in the eastbound lane and the second pass in the westbound lane. The inset on the lower left shows an enlarged view of the drive plan shown in light blue. As stated on the previous slide, each pass will result in a point density of 1,000 points per square meter on the pavement surface. With two passes, we will net approximately 2,000 points per square meter. At this level, detection of surface defects, deformations, and cracks will be very apparent in the pavement surface point cloud. Additionally, as with the aerial LiDAR acquisition, detection of surface defects, deformations, and cracks will require little or no field work or targeting. Using the GNSS results, sub-meter accuracies can be achieved. For this type of analysis, this accuracy is more than sufficient for PASER analysis. LiDAR processing, whether aerial or mobile LiDAR, consists of two steps in relation to the PASER analysis. The first is calibration. The raw acquisition scan data is processed in Regal's RI process using the post-process trajectory solution to produce a LAS point cloud. The point cloud is adjusted in RI process, solving for easting, northing, and elevation errors along with roll, pitch, and yaw errors. Each LiDAR swath is reviewed and indexed in the X, Y, and Z to the survey control if targeted control is set. If no control is set, the control will be indexed to known points, USGS elevations, existing survey control, or county LiDAR data sets. The point cloud will be reviewed for completeness, ensuring no clouds and voids are present in the data set. The second step in LiDAR processing is classification. An automated process will be utilized for classification of 75 to 80% of the LiDAR data. Upon completion of the automated process, experienced LiDAR technicians will complete a manual edit to classify any features not addressed during the automated macro processing. Classification is typically completed according to the codes in Table 5 from the USGS LiDAR Base Specification 2020 Revision A. The classification can be customized for the PASER application since the asphalt surface is the only critical data required. The LiDAR data can be processed to a colorized point cloud, which can assist in the identification of PASER deformations and degradation. The main image is a highway interchange in Florida. The inset image is a car ferry completed for the Wisconsin DOT. You'll see in the sample project shortly that the more tools available to the user, the better the quality of the PASER analysis. A tin surface, vertical color imagery, colorized point clouds, and intensity images can all enhance the abilities to see deformations, cracks, and asphalt pavement degradations. The LiDAR point cloud can be processed to a tin surface. This can be a useful tool to detect and inventory surface distress and cracking. The image below was extracted from the Ramsey County South Shore Boulevard project. The two circled areas depict denser cracking in the asphalt pavement, with some cracks easily wider than 1/2 inch. The tin model settings in this image show tighter settings and can be adjusted to exaggerate the vertical relief to provide easier viewing of these PASER features. The following slides will demonstrate how aerial and mobile LiDAR can facilitate the PASER ratings evaluation for several actual project corridors. Now we'll review some samples of actual asphalt distresses for several highway locations. The three panels below illustrate a small segment of South Shore Boulevard depicting views of the orthophoto, colorized point cloud, and black and white intensity image for the corridor. Each of these views provides valuable information on deformation and cracking along the corridor. The orthophoto provides a visual image of the cracking and patching among a few distress types. The color point cloud indicates a more precise view of the series of cracks and patching showing up as dark lines and patching. The black and white intensity image furnishes the best view of the distress cracking and patching, with very clear dark lines and patches showing up in the image. Since the LiDAR is referenced to a grid frame, county and state technicians can work in the office on a workstation to assess and inventory the PASER rating, whether small segments or averaging over a longer corridor. This eliminates a crew going out in the field, driving the highway, and trying to make these assessments to define a PASER setting. Further, this analysis can be made more precisely since each deformation, especially the more egregious ones, can be measured and quantified by the county and state technician, providing a more detailed analysis for a PASER rating. Oblique views of the roadways can reveal even more information on the stresses on the asphalt surface, especially if the vertical elevations are exaggerated. The upper left image represents an oblique view of the roadway without vertical exaggeration. The image on the right and the lower left image have the elevations exaggerated by a factor of 3 times. Different colorization also can reveal some of these distress issues. Notice the lower green shaded image clearly shows waterboarding stress in the asphalt surface. The three panels below show another small segment of South Shore Boulevard depicting views of the orthophoto, colorized point cloud, and black and white intensity image for the corridor. In a similar fashion as before, the three data types illustrate very useful tools that state and county technicians can use to determine an appropriate PASER rating for a portion of a corridor or average for longer segments of highway. Again, oblique views of the roadways can reveal more information on the stresses on the asphalt surface, especially if the vertical elevations are exaggerated. The upper left image represents an oblique view of the roadway without vertical exaggeration. The image on the right and the lower left image have the elevation exaggerated by a factor of 3 times. Different colorization also reveals some of these distress issues. As before, notice the lower green shaded image clearly illustrates a large sinking crack crossing the traffic lane in the forefront. The next sample is taken from Old Pasco Road in western Florida, where a fire station driveway enters the primary roadway. Mobile LiDAR imagery and oblique views of the roadway segment can reveal even more information on the stresses on the asphalt surface. The upper left image shows the area of distress depicting the series of holes in the asphalt pavement just outside of the fire station driveway. The right vertical and lower left LiDAR intensity images show a close view of how the heavy fire truck traffic leaving the fire station is severely stressing the edge of the asphalt lane. For the same road segment, LiDAR analysis permits the user to locate and identify the asphalt distress. The upper left panel shows a cross-section of the deep pitting in the asphalt surface. The right panel identifies the distress within the LiDAR dataset, and the lower left panel displays the image of the location of the distress. The three views below show a third sample of State Route 15 in Florida depicting views of the orthophoto colorized point cloud and black and white intensity image for the corridor. Although this is a concrete pavement surface, the primary concern with this corridor is cracking and the growth of seams between the concrete slabs. This project created a very robust example of the extent to which LiDAR can be used for PASER analysis. Oblique views of the same roadway can reveal even more information on the stresses on the concrete surface, especially if the vertical elevations are exaggerated. The upper left image represents an oblique view of the roadway without vertical exaggeration. The image on the right and the lower left image, as before, have the elevations exaggerated by a factor of 3 times. The different colorization also can reveal some of these distress issues. The patching at the intersection and entrance was completed due to subsurface utility maintenance activity. Using the collected mobile LiDAR, the seams and cracks in the concrete pavement can be mapped via feature extraction. This image is for the same sample set for State Route 15 in Florida. The methodology again will allow engineers and planners to see actual surface conditions in the field without ever leaving their office. The next 2 slides will show the level of analysis that can be done using LiDAR data on the pavement surfaces. This slide shows a utility patch on a concrete surface. The analysis begins with a colorized intensity image clearly showing the patch against the surrounding pavement surface. The second panel shows a horizontal cross-section defining the variation in elevation between the surface and patch. The third panel is a color image of the patch anomaly, and the last panel is a colorized point cloud elevation of the patch area and roadway. A seam in the pavement surface with a significant elevation shift between the 2 surface slabs. The horizontal cross-section depicts the elevation difference between the concrete slabs on either side of the seam. The shift in elevation is clearly evident in the colorized point cloud elevation panel on the lower right. Deformations on the road surface can be mapped and given a series of attributes suited to the user's purpose. They can be very simple or very complex. This example shows a variety of patches and cracks in the pavement surface. Each can appropriately be mapped with a polygon or line segment. The attributes can include the type of deformation, PASER rating number, the coordinates in X and Y for the deformation, and in the case of an applied patch, the date the patch was applied. There is no limit to the number of attributes that can be added and can produce a database of the deformations along a highway. A programming script can then be created to provide an averaging of the various deformations for any segment of highway via intersection to intersection or milepost to milepost. What conclusions can we draw from this presentation? From the PASER deformation definitions and sample projects provided in this presentation, it is clear that LiDAR data can be used to define and collect data for PASER analysis. Mobile LiDAR provides the best method for high-density point data to support analysis for PASER ratings for highway segments. Aerial LiDAR affords a lower-cost solution, but has to be acquired at a low enough altitude to attain a high point density for definition of deformations and cracks. A wider variety of datasets, such as imagery and LiDAR, provide the best practices for PASER analysis and ratings. Imagery allows you to identify the distress, while LiDAR furnishes the precise locations, dimensions, and magnitude of distress. Defining PASER ratings in the field is a labor-intensive process and is prone to incorrect assessments and averaging. Thank you for listening, and I hope you enjoyed this virtual presentation on aerial LiDAR and mobile LiDAR for use in PASER analysis and can take away some informative and new concepts on this emerging technology. Feel free to contact me with any questions that arise concerning PASER analysis and its implementation.
All right, thanks, Richard. Appreciate that.